If you don't already know me, my name is Marissa Torres, and I'm the acting program manager for Coastal Inlets Research Program. And I was also the PI of this particular work unit, focusing on practical modeling and wave response guidance for coastal structures using FunWave. And this has been a long journey in this particular work unit. Very thankful to my PDT members over the years, and the especially folks on the FunWave team and the students that we have had over the years to bring this to fruition, and not kind of towards the close of this work unit. So just to reorient and make sure I can, here we go. So the main goal of this work unit was to more or less define the numerical parameter equivalents that you would set in FunWave to replicate breakwater design that you see in the field or in laboratory, so in real life and in ways with the same basic structure parameters. Specifically, we were focused on a rubble mound trapezoidal breakwater to mimic those effects of a rubble mound trapezoidal breakwater, and the wave responses of interest were overtopping and run up, and then transmission and reflection. Wave transmission and wave reflection. And those are some of the concepts that I'll cover in this presentation. So ideally just trying to more or less, what do we need to bring FunWave to the coastal engineering table? Because it's not necessarily built for that environment. Well, it is. Let me rephrase. What do we need to make it easier to use FunWave for environmental assessment of coastal structure designs? Not contributing to the design itself, but how does that particular design interact with the wave environment in the near shore? Very specific. I'm not trying to contribute or change any design parameters here, just trying to make it useful. How do we make FunWave more useful for coastal engineering applications? More or less, that was my goal. From what I see on the call, most of these folks are familiar with FunWave. I've either trained you directly or I've seen you in another training. But for those who are not as familiar with FunWave, it is a nearshore wave model, a phase resolving Boussinesque type wave model that resolves. Is this playing? Yes, okay. That kind of resolves those nearshore processes. Specifically, we're looking at wave. Is this not playing? Oh, good if you did. Doing great today, guys. Well, it is a fun animation when it works. So the best place for FunWave is kind of in between kind of your 2D spectral wave models and your even higher fidelity full Navier-Stokes equations, or like your RANS models, or like your CFD models, computational fluid dynamics. It's kind of the in between there. It's where it works best in coastal areas where you have complex geometry and bathymetry that the spectral wave average models may not be able to accurately estimate wave diffraction, refraction, run up. Those nearshore transformations around that geometry. FunWave is pretty good at that. And then if you have more than say that FunWave is still not answering questions and you need something 3D, that's when you move to a 3D model. It just kind of depends on your area and like what you're looking for and what you're trying to get out of the model. So FunWave is a kind of a good in between there. It's computationally expensive. But we have access on our DoD resources. You're able to compute in parallel and run processes on multiple hundreds of cores if you want to on our high performance computing systems. And this was this is an open source model, so you can find it on GitHub. It's kind of controlled out of the University of Delaware, and there is a comprehensive wiki. So usually, if you do have a question, check the wiki first to see if you can find an answer. And then if you still can't find it, that's when you kind of come to us or submit an email to our user group, our Google group. Hopefully my other simulation, our videos will play. And if they don't, I'll try to find a local copy. Okay, so this has been a long journey. I have the project timeline on the bottom here. This particular work unit and focus kind of kicked off in FY22 when dollars came in, so mid-year around April 22, and we're actually going to continue through this fiscal year and into Q1 of next fiscal year to complete some things. I will also note that we actually took a break in FY24 because of the funding situation, and we didn't pick things back up until funding was available again in FY25. Funding and personnel availability kind of back this year. So that's kind of where we are. So in the previous years, what we have produced from this work unit towards practical modeling guidance, we do have 2 technical notes. The first one kind of focused on the beginning stages of getting comfortable with FunWave in general and using this type of model. So it's depth limited type model where there is a range of validity for where the model works best. So kind of describing those conditions, your starting conditions. So it's kind of like a reference for if my project area has these initial conditions where you want to start propagating waves, say on the, like you're not totally offshore, like not deep, but in towards your project area and a little bit beforehand, kind of give you a quick lookup as to, can I run FunWave here? What is it going to be good at resolving in terms of peak wave periods, for example? And then towards what do you need to consider for spatial resolution requirements and things to consider both on the physical level, so resolving the physical processes well enough. You need enough points. However, the numerical method can only handle so many points. And then there's towards that numerical stability. So towards that kind of info. In our next technical note, we get into some potential sources of instability. So with a phase resolving model, it's more challenging than our phase average. It's less stable and it will run into errors or it will blow up. So what are some of those common initialization errors to help you get started faster? What could be some causes of instability if you do have an error, and how to go about troubleshooting. So that's kind of the focus of the second technical note. That one came out last year, and hopefully that's helpful. I feel like because FunWave is a university open source code, there are things that have probably changed between when this came out versus the latest version of the repo right now. But I think for the latest stable version, these still hold. Naturally, things change as soon as you publish on them, right? It happens to everybody. Towards the wave response guidance, on the right-hand side is the full matrix of, not the full matrix, but it's the full range of what we wanted to more or less test or evaluate per wave response. And so we wanted to look at 1 and 2D, regular or monochromatic wave conditions versus irregular or the spectra conditions. We wanted to look in terms of structure properties, like its freeboard, the slope, the side slope of the trapezoid, its crest width, its crest height, and its roughness, because that is like that gamma F in the overtopping and run-up equations, for example. How does that relate to the CD in FunWave? Wanted to get to that. So this like full matrix, if I put it all together, yielding at least more than 10 million simulations, hence why it's taken a few years to get here. We've been doing over the course of this time kind of small batch test suites, and we've improved our ability to set up a functional test matrix kind of in a contained way, kind of a self-contained way. And I forgot to mention, Ryan Shanta is online. Ryan Shanta is online, and he's most recent ORI student who's been working with us, and he actually came up with the best method to kind of create these batch test suites, self-contained test suites for input and output post-processing that have significantly sped up our ability to go through this full test matrix. And he will be presenting some of the initial results today we have of wave reflection and transmission. So needless to say, this problem can get overly complicated very quickly on both just the numerical side, data storage, for example, all these files, simulation management, and then never mind trying to compare with literature and it's the correct assumptions and settings on the back end, like not even like disregarding the wave climate and structure properties themselves, but there's a lot that goes into, is this even possible to compare with literature? Are the same conditions met, kind of thing, or what kind of assumptions or averaging needs to be done in order to be comparable? So this has turned instead into a pure sensitivity analysis to wrap up the work unit. Now, this tech discussion is building off of a previous tech discussion that we did 2 years ago, and that one was with results from Levi Cass and Amy Bredis, 2 students we had that summer that significantly helped in the wave transmission response, especially comparing that across the 2 native methods to put structures in FunWave. On the left-hand side, you have like bathymetry modification. So that's just like putting in a breakwater right into your bathymetry, and that's treated as an impermeable surface. And below that, and on the right-hand side is the breakwater file, which is considered like your permeable breakwater structure. Now, the differences are that are kind of shown in the spectra, which are underneath each of those plots. So the bottom row there. In the spectra, you have blue is a gauge before the structure, and orange is a gauge after the structure, so behind it. And before is closer to the wave maker, so the seaward side. After is the transmitted wave train on the leeward side of the structure. And the biggest differences are in the way that the wave field responds. So even for a monochromatic, or a regular wave simulation, we have that dominant, that peak period that's shown in blue, and then post structure in the transmitted, that wave spectra, you see that energy in that dominant peak transfer to higher harmonics. So that's a dispersive effect, versus in the breakwater file, it's more or less treating like it's a fully dissipative effect, where you're seeing that orange peak is just has significantly less energy than in the incident wave spectra. So it's mostly purely dissipative versus dispersive. And so that was the biggest takeaway. And we we ran that for a bunch of different structure heights. So freeboard, relative freeboard with respect to the incident wave height for different friction. That's on the left-hand side for that bathymetry modification. And then on the right-hand side, we started playing with the two variables or two parameters that you can adjust to specify that breakwater file. And so looking at, well, if you sponge width, so how much space does that permeable layer, which is a frictional dissipative sponge layer internal to the model. Total width that it takes up in the space. These are just 1D simulations, so these are in the cross-shore width, and then the total strength. So if you're looking at the top right figure, it's kind of like a mesh, kind of be treated like a mesh, and that strength. So increasing the strength of the permeable layer is more or less increasing the like adding more. It's a finer mesh that the wave train has to go through. And in practice, we have learned that, and in theory and in practice, the dissipative sponge layer behaves the same as our bottom friction, which we can put on the bottom, our quadratic bottom friction. And it's more or less like acting on the full water column. It's water column because this is a depth average model, but there's still a difference as to where the bottom friction is applied in those equations. So it's either taking up the full, affecting the full wave train, or just affecting in that bottom boundary layer. And that's kind of what we wanted to investigate a little bit more, to remind myself. Yeah, okay. That's what we wanted to investigate a little bit more, is using more friction values and kind of comparing wave. We want to add on to this. This was just wave transmission, so let's add on wave reflection. And also really focusing in on the bottom friction and strength of the sponge layer, strength of the breakwater permeable layer. So wave transmission, how we're computing these is with internal wave stations. I'll show some later. I'll show a diagram of the domain and where we put stations a little later in this presentation. But for the most part, our wave transmission standard, energy transmitted versus energy incident, that ratio to produce a KT. And yep, and then for wave reflection, similarly, it's, it's the square root. Yeah, no, we do that. The energy reflected versus the incident wave energy. So that is based off of the Goda and Suzuki equations from 1976. And we used a talking with the Storm Sim team and mainly Abby and Jeff from our Storm Sim team or CHS team, expanding that analysis. It was expanded to 3 gauges by Kobayashi and Cox, and so we followed their recommendation. And per that paper, they per Goda and Suzuki, they recommend a spacing of at least 1/10 of a wavelength. So that's what we did. And I placed 2 sets of gauges, one set of gauges that are inside 1 wavelength from the toe of the structure, and then 1 set of gauges spaced as such outside 1 wavelength from the toe of the structure. And so that scales with as we change the wave conditions with period and water depth, that's going to scale. Those placements will scale with that. That's wave reflection. That's how we did it. In terms of the test suite that we'll talk about today, we do have so this full test suite in the upper right-hand corner for the ones that are not grayed out. That is the full test suite of all the simulations that we would want to do in the full test matrix. For this study, we initially reduced that to just periods 2 through 8, following that curve of what our range of validity, as well as meeting our numerical stability and spatial resolution considerations, following that curve. For today, we also reduced that a little bit more to what is in just that blue box for the most part. So I think some will have the full from 2 to 8, and some will be reduced, because we did find an error earlier today, and we wanted to redo as much as we could to be able to provide you with some results today. We're doing our best, guys. So what we kept constant in this case is the relative wave height, relative freeboard, and relative crest width. And we have 4 sets of simulations, 5 sets of simulations. A flat tank, nothing in it, no friction. Flat tank with just bottom friction. Flat tank with the sponge, just the sponge layer. And then we have with the structure, a naked structure. I don't think we're going to talk about that one today, but we do have like that naked structure, as well as structure with bottom friction added, and then structure with the sponge layer on top of it, so with the sponge layer added. And we kept the sponge width constant. More or less the sponge width is constant, as it's the same toe-to-toe width of the structure, but the toe-to-toe width of the structure does vary with wave condition, because that is a function of of the space that it takes up in the water column, based off of your period and water depth. So I think with this, I turn it over to Ryan to talk more.
Hello, everyone. So this is some preliminary results. Hopefully they'll play. And this is also partially just showing what wave propagation in this framework looks like. So on the left is very small BWAC value in a flat tank, and then you can see the effect of the breakwater on the right. So more or less the design product that we're looking to deliver to you is choosing these BWAC values and how they affect the hydrodynamics for your different problems. So one of the other things we're looking at as well is in the region labeled BWAC, which is the breakwater absorption coefficient, one of the FunWave parameters, is how does that compare with just using bottom friction? Because these are not exactly trivial questions when you're setting up the model and you have all of these different options in the inputs between whether to use breakwater, friction, both, sponges, and they have different effects on the hydrodynamics and different strengths as well. And it's also difficult to compare these to the literature as well, just because there's not a whole lot of body of literature for a wide array of problems. So this report is more or less a sensitivity analysis for these common breakwater scenarios that you might see in FunWave, and how that strength varies throughout the parameter space as a function of hydrodynamics, geometry, and then, of course, the parameterizations of the physical processes on the bottom. So all in all, the variable space has about at least 7 to 10 dimensions, even for this flat tank. So mainly, we're just exploring those and trying to find regions where you might want to use one over the other, and such. So yeah, that's all I had to say about this slide, I think. So this is some preliminary results, and I use the word preliminary use the word preliminary there because there's still a lot to be done here. But one of the interesting things about adjusting CD or BWAC throughout the entirety of the tank is that it may have a smaller effect than you might think on something like reflection. And this is something that is not necessarily reported to our knowledge extremely well in this sensitivity analysis. So on these plots here are the reflections as calculated by the Suzuki Goda model. And you can see that there's clearly some dependence on hydrodynamics, so KH, the dispersion parameter. that either brings it up or down, but it doesn't actually vary a whole lot with either CD on the left or the breakwater coefficient on the right until you get to relatively extreme values. And these values here, if you were to zoom in a little bit, you would see that they do vary a little bit more on the tails. It's a little bit hard to see here just because of all of the sheer number of simulations run. But there is some clear patterns within each KH band as well. So this is helpful to know in terms of just setting up and making sure that reflection is sensible within your problem domain and what you could expect given a given CD or breakwater absorption coefficient.
Right, and I would add to that so this is without a structure. This isn't just an empty tank, but we put that section of bottom friction or the permeable sponge layer in the tank. And I think like the biggest thing that I noticed is there's even just reflection. Just if you let the simulation run, there's of course some level of reflection from the numerical boundaries that are there's only so much that you can do to completely dissipate all the waves in the tank. So this is with sponge layers on the ends, on the boundaries, even with a monochromatic wave here, you still have some level of reflection, and the percentage kind of changes a little bit with KH, but for the most part, you see that range anywhere from 70% to 50% wave reflection in an empty tank. And that band kind of narrows for the higher KH values. So higher KH is your longer wave periods in deeper water versus lower KH is your all range of wave periods, but in more shallow water. So that's kind of what we're seeing from dark to light. There is even some level of trend or no trend from what I'm seeing. So this is on a log scale on the x-axis. And so this is going from 0.01, 0.1 to 1 in terms of value with scaling in between. And I think what's interesting here is even in an empty tank, there is very minimal change in the wave reflection response between that 10 to the -2 and 10 to the -1, which is your 0.01 to 0.1, which in the literature, in some cases, depending on what you're looking at, there's a lot of quadratic drag coefficients are in between that range or are in between 0.1 to 1 in that latter section. And we're actually not seeing really, there's not much change in that wave response, at least for this metric, for example. So I always thought that like a CD value of like 0.002 seemed completely negligible, and for the most part, I feel like it is. Even 0.02 might not be not doing what you think it's doing. So it's not actually having as large of a response as, I guess, what's been the relation of what's been measured or calculated, and in the published literature, it's not the same as what I'm seeing here. I'm not trying to throw any daggers, but I'm just noticing that the response, you really only start to see that response closer to a value of 1, where you see more of that downward trend having less reflection, and here having a slight upward trend where you're getting more reflection when you're increasing the strength. All right. I'll pass back to Ryan.
And this is also a similar plot, but with the structure in place, showing how reflection varies throughout the logarithmic range of either CD or the breakwater absorption coefficient. And you can see that overall, the ranges are somewhat comparable. One is not greatly different than the other. They're in that same band centered around about 0.5. And there's also that clear pattern in hydrodynamics with a bit of a stronger pattern for CD, especially towards the left or towards the greater values of friction. So overall, these trends mirror pretty closely what you would get without the structure, but they are slightly different. So as a design tool, again, this is something that would potentially be good to be aware of as you're setting your CD and BWAC values, whether or not to use CD, BWAC in conjunction with the structure, because you essentially have 4 different options when you consider the structure, the flat tank, CD, or BWAC. So being able to explore this parameter space and have an understanding of what it does to the hydrodynamics behind the structure could be important in the design process. And Marissa, do you have anything to add to that?
I would add that this was our late discovery problem child. So please do not put too much weight in exactly what this right side of the graph is saying. Don't look for the man behind the curtain. We noticed an error in the simulations, and this is what we're rerunning in order to form more of these relationships. So with friction, this is with friction with the structure. So if I jump back and forth, right? So we are seeing in just the flat tank that range of reflection coefficient was between like 50 to 70% reflection, and it was narrow. Versus adding the structure, we have more a range of 40 to 80% reflection possible, with more of that center line or the mean being closer to 60% reflection, and that the total spread was larger. And like Ryan mentioned, we see more of that decrease in, or that decreasing trend between 0.1 and 1. So 10 to the minus 1 to 10 to the 0. Kind of, sorry, I have cursor in here, right? More of that downward trend. We will see. We'll confirm if this holds, if this relationship holds, or if it behaves more like the bottom friction. My apologies that this was on me for not having this fully prepared for you guys today, but I did want to give everybody an update. Thank goodness CSRM is also this week, and there's not 50 people here. Anyways, wave transmission. All you, Ryan.
Okay, so again, the right plot is kind of our problem child plot for the moment, just because of a last minute BWAC error and processing. But the left plot is particularly interesting for showing the transmission coefficient as a function of CD, so the bottom friction for various hydrodynamics. So as of right now, we're still teasing apart what relationships may linger within this plot on the left to see if there's an easier way to predict exactly how this hydrodynamics is going. Because as of right now, you can see this kind of a rainbow of colors with not a clearly discernible pattern. So we're looking into some correlation analysis on various input parameters, and both for the geometry of the problem, the hydrodynamics of the problem, and then potentially also some of the other numerical FunWave settings. So overall, this trend for wave transmission, it's a breakwater, I think overall makes sense for what you would expect from this, with higher values of friction, doing more to reduce the transmitted wave amplitude going through. So this, again, is helpful in designing the breakwater, because with the structure and with a high value of friction, you can really get pretty low transmission rates. And anecdotally, so far it's not on the graph, BWAC also does a pretty good job at this as well. And the end product will be comparing these two to kind of see what happens in the parameter space. And of course, this parameter space here for transmission, this is just kind of one snapshot of a very specific freeboard width of the structure and slope of the structure. So in theory, as we continue building this matrix, we can hopefully provide design guidance for different geometries of standard trapezoidal breakwaters, and provide some recommendations as to what kind of wave transmission you might see from those breakwaters. Because as of right now, it's not a super well explored parameter space when you consider just the dimensionality of it. But hopefully we can get forward and provide tools that could be useful to those users of FunWave that are ultimately looking to calculate wave transmission for nearshore projects.
Great. Agreed. Nothing more to add there. Okay. So I can cover this. So initial discussion, as especially like this helped us kind of figure out that we had an error in the results in the first place, is in these comparisons. I think I forgot to mention, in order to compute the energy transmitted versus energy incident, how that's computed is with those virtual gauges with that certain spacing that generates a high temporal resolution time series that we then provide or do spectral analysis on through FFT and sum that total energy to get that total energy in the power spectral density function. And one thing that we thought these results could be sensitive to was the selection of the time series taken from the simulation in the spectral analysis to compute those metrics. And we investigated a few different cases where we take the whole time series, we take just like the back half of the time series where you would anticipate more of a steady state, and you can have the same time slice for each station in the file, whether it's closer to the wave maker or closer to the end of the closer behind the structure, more or less, and kind of in between. So monitoring, okay, well, how long did it take the initial perturbation to reach certain segments of the domain, and how like adding or counting like how many wavelengths to include or to take from that time series to put into your FFT. So we investigated a few of those, and we actually found that it had minimal impact on the response metrics. So that could either be a good or bad thing. So I think it's probably lending towards the good side, where I think our post-processing routine is relatively solid. There's no change regarding or whether or not you have any certain length of the time series is in there. I think our post-processing methods are good, and I think that bodes well for in terms of guidance when we do eventually provide these post-processing tools as scripts and deliver them to the field, that recommendations for which part of the time series to include may depend on which metric that you're looking at and what your domain looks like, but for the most part, you can use either the whole time series or the back half, and you wouldn't get too much of a different response. Second, I mentioned that we had two sets of wave gauges or stations for wave reflection. One was inside one wavelength from the toe of the structure, and one was outside one wavelength from the toe of the structure. And differences between those were actually pretty minimal for this regular wave case and for these cases that we ran. So I think that also bodes well to our reflection script. And I think in general, our spacing was consistent across both, but there could still be some sensitivity to the spacing that we did not investigate. And in this particular study, we just kind of went off of what was recommended from Goda and Suzuki. And I know that there are some instances of like optimal gauge spacing for wave reflection that we just we don't have the capacity to kind of leverage or the capacity to complete in this work unit right now. Right, so we kind of talked about how the range of reflected wave energy and reflected wave energy, how that varies between the flat tank, the total range of expected versus with the structure in place. We already kind of talked about that, and then Talking about those tails, where we're getting by tails, I mean in the spaghetti pots closer to a frictional value of 1.0 or 1, that rate of change between the bottom friction and the permeable BWAC or breakwater absorption coefficient is different. So it's either increasing or decreasing. Like, is the BWAC, is the wave reflection and wave transmission response with the permeable layer, with the breakwater layer, is it changing faster or slower than if when you have just bottom friction? And that's like really towards the answer that we wanted to have, right? So I mentioned, like, in theory, it should have the breakwater permeable layer should be more dissipative and reduce the wave response more quickly than with just the breakwater. I'm sorry, with just the bottom friction. So once we have all of those things, I'll provide an update to everybody, and we'll be able to confirm that more or less, or like see what we're seeing or describe what we're seeing. All that to say, oh goodness, I did take a long time. All that to say, so for Ryan, if you want to quickly go over some of the additional guidance we were able to tease out of some other test suites that we were working on earlier this year.
Yeah, sure. So this builds off, or this is just a repeat of one of the other presentations we gave a few months ago to a smaller audience, more or less just investigating for an arbitrarily long tank. How does the wave energy transform and either be conserved or not conserved over the length of the tank? So one of the main things from that was just for very large domains, a lot of wave energy might get kind of eaten up by the numerical scheme just due to how highly nonlinear some of the spaces in the variable, some of the combinations in the variable space can be. So this is also potentially useful design guidance for especially setting an offshore condition. For some cases, it might be more beneficial to have the wave maker closer to your design area, just to make sure you're not losing energy before you want to lose the energy, essentially. So this was more of just a sensitivity analysis for the nonlinearity of the process here. And on the right plot, there's this maximum distance that maintains 90% of the wave energy. So for all of the parts as the color bar goes up to that about 10,000, those are all cases where you don't really have to be all that careful about the size of your domain and potentially losing energy for highly nonlinear waves. But as you go into the limit of the shallow water region on the bottom right, or to the extremely nonlinear on the bottom left, you can see those contours are kind of battling each other. Then you might have to be a little bit more careful about the size of your domain and the way your waves are behaving as you're doing other things such as transmission or reflection, just because it's just another process that the user should be aware of as a mechanism for where energy is going and how waves are transforming within the tank. And the plot on the left shows more or less the same thing in a different perspective, just as a function of energy. And you can really see as that KH value goes down, you have to be more and more careful about applying your energy conservation and kind of metrics based on energy, such as transmission or even reflection. And this is another kind of plot just showing the exact same idea here as well, where for extremely shallow KH, so this would be a highly nonlinear wave where the nonlinearities are actually essentially winning over the dispersive effects. You can see that you could rapidly lose energy within the tank, especially as you go down to about that 0.14, or really below 0.2 overall. If you're more than about 10 wavelengths away from the wave maker, you're going to rapidly be dissipating energy in a way that's not necessarily physical or controlled with what you might expect through braking or other processes.
Yeah, and I think, Ryan, we had a separate conversation with Matt and Feng kind of going over this, and it's more or less just due to that high frequency noise in the wave spectra that's just not captured. Question mark.
Yeah.
Yeah, so that's what we worked on this year. And my animations didn't go very well. But here's everything, focusing on the left-hand side. So looking ahead, Q1, trying to wrap all this up into a nice little bow. We're going to go through, find any remaining errors, get those squared away in with our little small batch matrix method. So first thing, can we investigate more of those frictional values, maybe between 1 and 2, since that's where we're seeing the most change start to occur. So how does that continue through larger friction values for both, and repeat all these, repeat this analysis or a modified test matrix for the other variables of interest that we want to analyze the wave responses for. Do the same for run up and overtopping, just finishing what we haven't yet finished, again, following that small batch method, and hoping to prepare the comprehensive draft technical report covering the sensitivity analysis for all of these wave response metrics. Hopefully by Christmas, maybe a little bit after New Year's, we'll have that wrapped up, and I'm hoping to at least get it into the publication process by February for an April publishing date. Fingers crossed, as well as formalizing and distributing our post-processing scripts and archiving the fund data. Beyond that, we kind of want to assess remaining needs. This is the last year of this work unit, as well as the other FunWave work unit under CIRP at least. And so going back, I just want to, I guess I'll double check with folks who submitted these statements of need that are kind of FunWave, either directly related to FunWave or tangentially related to FunWave, and see what did we miss, what weren't we able to get to for these statements of need, and kind of is there a way that we can address these in the future, and what might be the best method. I feel like we learned, and by we, I mean me especially, but the whole FunWave team learned a lot in doing this sensitivity analysis and trying to use FunWave in this way, and like really digging into certain variables. And especially with other recent updates that are ongoing, because it is an open source code and academic code, our lessons learned also aggregated and turned into, like, we really need an internally managed model code, so that way we can control the updates with any updates that come from academia that are pushed to the main repo, and just having our own version to be able to control in-house. That I think will remove some things that USACE folks don't necessarily need, and kind of simplify the whole process, and also clean up the code to make it easier for management and updates in the future. Hoping for a FunWave USACE type thing, and really looking towards Mike and Ryan to help with that. I think that would be alleviate some of the burden in bringing FunWave, or having FunWave be more operational and useful for the field. Otherwise, it's kind of an uncertain future. This year has been an unprecedented year all around in terms of administration and lab priorities. We would love to grow the FunWave team, looking for folks, but still have that ongoing hiring freeze. And I just do want to let you all know, since I've been in this acting role for the CIRP for this program, I may transition to a full-time PM role in next quarter, so at the start of FY26, and I do plan on, in order to help wrap, like if that happens, I do have a plan to help wrap this up. And even Dylan Robinson, also on the line, I've been working with him on FunWave things this year, and hoping he's able to take kind of chip away at these remaining items, and help push the sensitivity analysis over the finish line. So it's been a wonderful time, more or less, like through this whole work unit. I didn't get all the pictures that I wanted to get in here, but just shout out to everybody who's contributed to this work unit, especially PDT members as well, who have been there the whole time, who have been consistent and have provided a lot of feedback. I do want to thank Matt and Tanya. Tanya's not dead, but she's gone from USAE. So I do appreciate her giving me an opportunity, or giving this team an opportunity to challenge FunWave in this way, and kind of provide some of that initial guidance, practical modeling guidance, and some wave response guidance for you guys in using FunWave more efficiently and effectively. And I just really appreciate my time with the FunWave team, and going out to districts and helping with FunWave workshops as well. And I hope that this has been useful, or this the products of this work unit are useful in your everyday and in your day-to-day, and I hope they continue to be useful. Either way, I appreciate your time. Thank you all.